full detailed run through, but basically you have this propped cantilever circular ring. So it's indeterminate by 1 degree because you have the fixed support at A and a roller support at B. An applied moment at the free end. And so the process is the same, right? Since it's 1 degree indeterminate, you're going to choose one reaction to relax or one support to relax and replace it with a constraint force. So in this example, I released the roller support at B and replaced it with a vertical force. And then you require that displacement to be 0 in order to solve for the reactions. We have 2 regions to write moment equations for. So from the first region, you're going to, I labeled them 1 here and 2, and then I looked at region 2 first. So some moments about the cut to determine the magnitude or the equation for a moment in that second region, and it's just going to be constant equal to the applied moment at the free end. So anywhere between B and C, the internal moment is equal to negative m naught. And then in region 1, you have the force at B to include in your moment calculation. All right, and so that one is going to vary with respect to the angle. And this example also features a variable change. So this is done for convenience purposes. You don't have to do this, but at this point, it was convenient to define an angle theta in terms of phi. And so here I've got the moment expression in terms of either one. And then when you go to set up the integrals, right, for region 1, so region 2, I'll say, right, is just going to be not contributing really because the partial derivative of region 2 moment with respect to the force at B is 0. So ultimately this does not contribute. Region 1 is where we're going to get all of the data from. And so that's integrating with respect to phi right now is how we have it set up. From pi over 4, which is B, to A, right? And then going through that, let's see. So I set it up in terms of phi and then went through the variable change here for convenience. And so when you do that variable change, you just have to remember to also account for how that's going to affect the d phi d theta relationship, right? So in this case, it's just a negative sign that gets introduced. So then setting that deflection at B to 0 and integrating to solve for FB, determine that force, that reaction force in terms of the applied moment as well as the radius. And then from that you can determine the more specific moment equation, right, in terms of the applied moment and plot the values. So here in region 2, this was the free end C, here's point B, and then here's point A. Region 2 has a constant moment, and then in region 1, you have a varying moment, but it's never going to reach 0. So in order to find the maximum moment in region 1, I would recommend either plotting it like it's done here in the example and determine what the maximum is from the plot, or if you don't feel like plotting it, you can mathematically check it by solving for any local maximum value, right? Looking for where the slope is 0. And also comparing that to endpoints, right? Because here the local maximum is smaller in magnitude than the endpoints. So you got to think about all of those things, right? Questions? Okay. Alrighty. So moving on, torsion. You guys have seen torsion in mechanics of materials. Oops. Here it is. Okay. All right, so in mechanics of materials, you probably saw torsion of circular shafts, hollow or solid, and you also looked at maybe torsion in thin-walled sections. Does that sound right? Maybe? I think, at least when I taught the class, we did that. All right, so in this class, we're going to focus on torsion of non-circular shafts, right? So the equations that you may be familiar with for torsion, where shear stress is equal to TR over GJ, that is accurate, that is exact for circular sections. For non-circular cross sections, we have to use an approximate method, so we don't get an exact solution. And so this first lecture is going to be the tedious one that goes through all the math behind that. And then after this lecture, we'll start applying it to different types of non-circular cross sections. So here, let's go to purple. We've got a rectangular cross section, right? And we're going to define a warping function in the cross-section plane. So if you imagine a rectangular cross-section, like if this piece of paper represents the cross-section and it's experiencing a torsion or a twist about the longitudinal axis coming out at you, in that cross-section plane, the corners will bend in and out. So there will be deformation in the axial direction on the corners. And so that's what we're defining with this warping function. So we'll define the axial deflection. We'll say lowercase u is equal to theta times the capital Greek letter psi, which we're using as the definition of the warping function right here. And I mistakenly wrote x and y. It should be y and z up here. So psi is a function of y and z. Since it's in the cross-section plane is the yz plane. All right, so theta is equal to, that's defined as the total angle of twist, which is phi, divided by x. So theta effectively represents the angle of twist per unit length of the element. Also in the x direction. Now you can also think of it as the rate of twist. So if we consider the positive YZ quadrant of this cross-section and then zoom in on it in the YZ plane, let's consider a point within this cross-section before any twist is applied. So this point here is before twist. And then when a torque is applied, that point, if we're applying a positive torque, will move, right, somewhere, it'll move counterclockwise, so something like that. So that's its location after twist. And we can break that down as, bless you, a change in the Y direction and in the Z direction. So we'll call the change in the Y direction W and the change in the, the change in the Z direction W and the change in the Y direction V. So R stays the same. And R is the radius to that arbitrary point. Measured from the centroid. So if we zoom in on that geometry, all right, where W and V are changes in Y and Z. This side would be R times the angle phi, right, which is the total amount of twist at that location. So we can define V and W in terms of R and phi. So this angle alpha is specifically to the original location of the point, right? And Y and Z represent, the variable Y and Z represent the coordinates of that point before twist. So the change in Y, which is V, I'll just note that, that's our delta Y, is V. That's going to be negative R phi times sine of alpha. And we can replace sine of alpha with Z over R. So that's negative R phi times Z over R, which is negative phi Z. So we can say V is equal to, now we'll substitute in theta equals phi over x. So we can say this is equal to negative theta times x times z. . our change in z being W can be represented as R phi cosine alpha or R phi times y over R or phi times y. So we can say W is equal to theta x y. And so at this point, I'm just going to note, all right, we'll use these on the next page. Why are we going through all of this? Well, ultimately, it's to define shear strains, right? So remember back in the beginning of the semester when we did something similar for a plate that was undergoing translation and rotation, it was undergoing translation and deformation, right, shear deformation. And we defined strains using the partial derivatives of u and v and x, u and v and, what was the other one? I guess it was just u and v, right? So we're doing the same thing here. So the partial derivative of v with respect to x is negative theta z, and the partial derivative of w with respect to x is positive theta y. So now we'll go through and evaluate the shear strains using these relationships that we just outlined. So we have 3 shear strains total to consider, right? We'll start with the shear strain in the YZ plane. So that's going to be the partial derivative of W with respect to Y plus the partial derivative of V with respect to Z. So that's going to be theta x minus theta x, or 0. So that tells us that there is no distortion in the cross-section. In the YZ plane. For the xy, we have the partial derivative of v with respect to x plus the partial derivative of u with respect to y, right? And we defined u up above, where u is that axial deflection, and we use the warping function to define it. So here, and we haven't yet defined that warping function fully, so and ultimately we won't really have to, I think. Yeah. So we're just kind of using that to set up the rest of the derivation. So this is going to be theta times the partial derivative of the warping function psi with respect to y minus z. So we can say the shear stress in xy is equal to g, shear modulus, times gamma xy, which is theta times g times the partial derivative of psi with respect to y minus z. And then similar for the xz plane. Here we have the partial derivative of u with respect to z plus the partial derivative of w with respect to x. And that's going to be theta times the partial derivative of that warping function with respect to z plus y. So we can say shear stress in the xz plane is equal to shear modulus times gamma xz, which is theta times g times the partial derivative of psi with respect to z plus y. All right, so like I said, we didn't fully define this warping function beyond saying that it's a function of y and z. And that's because we're going to eliminate it so that we can move on and define another function that we're going to have to ultimately work with, right? So we're going to eliminate that warping function using algebra. So we'll take the partial derivative of the shear stress in the xy plane with respect to z minus the partial derivative of the shear stress in the xz plane with respect to y. And this is chosen intentionally to eliminate that warping function. So that gives us negative 2 theta g. Right, so just subtracting this equation from this equation, we're left with 2 theta g. And so now we can go ahead and define a stress function. So we're going to say that the shear stress in xy is equal to the partial derivative of, we'll use the capital letter Greek letter lambda with respect to z, and the shear stress in the xz plane is equal to negative partial derivative of lambda with respect to y. Now, if we make those substitutions into this equation, a question or?
I've never seen that variable.
The lambda?
Yeah.
Yeah, you're probably used to seeing it like that.
Yeah.
Yeah, this is just the capital version of it. Yeah, looks like a hat. All right, so making those substitutions now, we have the partial derivative, second partial derivative of lambda with respect to y, plus the second partial derivative of lambda with respect to z is equal to negative 2g theta. So this right here is the general solution for non-circular shaft torsion. In order to solve problems, we would have to apply boundary conditions. And also, right, lambda is still just a big question mark right now. We haven't gone through the process of finding what that is. So that's going to be our next steps. All right, so on the next page, we will start to define properties of lambda. using the ubiquitous kidney bean shape for a cross section, right, to represent a general non-circular shape. And if you consider taking a slice, right, in the z and y directions out of this volume, which is taken as a finite length dx along the axis, on the exposed surfaces of those cuts, we would have an internal shear stress in the x direction on the y face, and we'd have an exposed internal stress in the x direction on the z face. So for equilibrium, right, we know that the exposed forces on those faces are going to be the integral of the shear stresses over the area over which they act, right? So we're going to use that information and apply equilibrium. So the shear stress in the x direction on the y face, which is this one, times the area over which it acts, which is dz times dx, and then in the other face, we have the shear stress going in the opposite direction, so minus the shear stress in the xz, so that's the x direction on the z face, times the area over which that acts, which is dy times dx, is equal to 0, right? There are no axial forces, there's no bending, so there's no net normal stress to contribute to that direction. Those are the only components in the axial direction that are causing forces internally, right? And we know that equilibrium must be satisfied, so they're equal to 0. So if we consider this equation, right, we have dx showing up in both terms. So we can eliminate that. We know that dx is not equal to 0, right? And then if we define the change in the circumference, ds, right, bring that into the picture, and divide all sides by ds, and we have tau xy times dz over ds minus tau xz times dy over ds is equal to 0. And then applying our definition from the previous page here, all right, so tau xy is partial derivative of lambda with respect to z, tau xz is negative partial derivative of lambda with respect to y. Making those substitutions here, we have partial derivative of lambda with respect to z for tau xy times dz over ds plus, right, so we had a negative sign in our substitution, so now plus the partial derivative of lambda with respect to y times dy over ds is equal to 0. So now we've got our dy's and dz's canceling out. So we can conclude that the partial derivative of lambda with respect to the circumference, right, the outer edge at least, is equal to 0. What this means is that lambda, this function, is constant along the outer edge, right? So it's not going to vary on that outer edge no matter how far that edge is from the centroid, right? So even this point, which is a lot closer from the centroid, it will have the same value of lambda as this point over here. So I'll summarize that. Lambda does not vary on the side surface. Of the shaft. So, for simplicity, we're going to go ahead and set that value equal to 0, right? If we know it doesn't vary, it's a constant value, it's just going to be easy for us if we set that equal to 0 and make that our baseline. All right. So now, if we say lambda is equal to 0 all along the outer edge, let's think about what's happening on the interior. So again, looking at this ubiquitous kidney bean shape in the YZ plane, we'll consider a finite area, dy dz, or dA, with shear stresses tau xz and tau xy acting on that finite area due to the applied torque shown here. So y and z are measured to the center of that finite area dA. I guess I wrote that down here below, so we've got that note already. So if we want to relate the torque to our function lambda, which is our next step, we can say that the torque is equal to the integral over the area of the shear stress tau xz times the moment arm to that shear stress, which is y, minus the shear stress tau xy times the moment arm to that resultant shear stress, which is z. So now substituting in our lambda definition, we have negative integral over the area of the partial derivative of lambda with respect to y times y plus the partial derivative of lambda with respect to z times z. And then we can write that as double integral of partial derivative of lambda with respect to y times y dy dz minus the double integral of the partial derivative of lambda with respect to z times z dz dy. All right, so just separating those terms and applying the order of integration that makes the most sense for those terms. So then integrating by parts, we would find that the torque is equal to 2 times the integral over the area of lambda dy dz. So what this means is the integral of our stress function lambda over the entire cross section is equal to half of the applied torque. Also, thinking about the edge, right? The derivative of lambda in the normal direction to the edge will be equal to the shear stress at the edge. So at the outer edge, we have the shear stress defined as shear stress in the normal tangent direction with respect to that specific point. And so that shear stress will be equal to negative partial derivative of lambda with respect to the normal direction. So this is all leading to the membrane theory of torsion. Basically, lambda represents an inflated membrane that is applied over the cross-section face. So if you just imagine a inflated sheet or balloon or whatever, soap bubble acting on top of this surface. The magnitude of lambda, right, so if this is the flat edge of the surface, the magnitude of lambda will represent, take that back, the slopes of the function lambda at any given point will represent the shear stresses directly below, right? And so then the magnitudes of that lambda tie into the volume, right, that will be underneath the membrane, and that's what's equal to half of the applied torque. So as we mentioned earlier, right, we already established that lambda is constant along the outer edge, right? That was from the previous page. It doesn't vary. And so if we set that magnitude equal to 0 on the outer edge, we can readily calculate the volume under that membrane and relate it to the applied torque, right?
Neat. There's no shear strip, or there's no shear on the edge of something, right?
Right, so the free edge of a cross-section, well, that's true for vertical shear. Yeah, for vertical shear. For torsion, it's different, right? For torsion, you're going to have the maximum shear stress on the outer edge, 0 shear stress at the centroid. Yeah. So on the next page, we have a handout with different non-circular cross-section shapes and some related equations and relationships. So here you've got the shear stress at the, points of interest on an ellipse defined, as well as the rate of twist, theta. For the triangle, I think the triangle is a little more interesting. So here, remember the membrane function we defined it as having 0 elevation at the boundaries. So that means there's not going to be any shear stress in any direction at a sharp external corner. Because if you think about, right, consider, right, these two sections and compare them to a circular value that would hit the same points. Let's see how well that does. Kind of good. Right, compared to this hexagon, if we were to transcribe a circle that would fit inside, there's a lot more material in the triangular shape that's basically not participating much in the torsional resistance at all, right? So smaller interior angles, like the triangle, would be less torsionally active in response to an applied torque. So I'll note some of those relevant items here. All right, so basically what it comes down to is these non-circular cross-sections are less efficient, basically, than a circular cross-section. Oops. All right, so I'll stop there because we're out of time, but I will have next time some more comments on the rest of this handout, specifically this table here and how to use it, because you'll need to use it for your homework once that is assigned for this segment. Okay, any questions? All right, good deal. So I did post the next homework assignment. I forget when I said the deadline was. I think next Friday. Yeah. So originally on the schedule, I had it slated for next Wednesday, but I figured I'd push it out to Friday. I think it just means it's going to be a little bit crunched on the next assignment because the following Friday is Veterans Day holiday observed, so we don't have class. So just have that due. I don't like having assignments due on holidays, so yeah.